So, last time we have considered irrotational solenoidal part of the flow, that is that part of the flow for which the divergence is 0 as well as the curl is 0. Since the curl is 0, this velocity field can be expressed by a scalar potential, and then that scalar potential satisfies the Laplace equation. We have discussed some general properties of the Laplace equation and consequently the general properties of the irrotational solenoidal flow field. We have also discussed that uniqueness condition in a singly connected domain, and we have seen that the irrotational solenoidal flow field can be determined uniquely if we know or if we specify the normal component of the velocity on all the boundaries, or the potential function itself over all the entire boundary, or a combination of the two. That is, the normal component of velocity specified on some part of the boundary and the potential is specified on the remaining part of the boundary. Altogether, it implies that in any case the boundary condition must be specified over the complete boundary, which is said also is a requirement for the solution of Laplace equation, or in general in any elliptic partial differential equation, that the solution of an elliptic partial differential equation can be obtained if the boundary condition over the entire boundary is known. Knowing only on the part will not be sufficient, we have to know it over the entire part of the boundary. Next, we will see it for not singly connected domain, or rather the multiply connected domain, when the flow field is multiply connected. We earlier mentioned that in the singly connected domain the potential function phi is a single valued, but it is not so or need not be so in a multiply connected domain. This comes from the very simple fact that in a singly connected domain, if we join 2 point by say 2 path, say any 2 point O 2 p by any 2 path, since the domain is singly connected, this is a reducible curve. That means, we can shrink this curve, this closed path to a point, and consequently these two curves together forms an open surface, and we can apply Stokes theorem to it. That is, the line integral of the velocity over this closed path is same as the curl of the vector field, the velocity in this case, over this surface. And since the curl of V for irrotational solenoidal flow is 0 at each and every point, that surface integral is 0, meaning that the complete line integral is 0. Okay. That is what we took it, that V dot dx is curl of V in dA. And this is 0 and from this we concluded that since this V dot dx is same over all the path. So, V dot dx, which is the difference in phi from one point to the other, is same over all path. So, as we move from O to P, whatever path we take, the change in phi will be same. Consequently, the p phi at P is also same. whatever path we follow, or the potential phi is single valued. This is in singly connected domain. Or singly connected region. What happens it is, if this region is multiply connected, then we cannot shrink this closed curve to a point without going out of this region. Let us take that. Think about, we have an infinite circular cylinder or any object. So, this is another, say this is a boundary, this is not just a curve, this is a boundary. Now, if we have any 2 points, say O 2 P, so this is one path and this is another path. Now, if we try to shrink this curve, and even if we translate it to another side, we can never shrink it to a point without crossing this inner boundary, interior boundary, and when you are crossing the interior boundary, of course, we are going out of the region, because this part is not within the region. Okay. This part is not within the region. So, we are going out of the region and we cannot shrink it to a point. This is not a singly connected domain. Then even though we now have a complete circuit integral over this closed path, we cannot equate it to this right hand side. Okay. And we cannot say that phi is single valued. In this case, we cannot form this open surface over which we can take this surface integral, this right hand side of this equation. We cannot have such a relation here. So, Stokes theorem, this is what is Stokes theorem. Is not applicable for the irreducible curves. But remember that still, if the if this path is reducible, like think about another path here from these 2 points, we can have this type of path. So, in for this case again we can apply. But for these paths we cannot apply it. So, phi or the velocity potential is not necessarily single valued. It may be single valued, it may not be. Now, before we proceed further, let us say a few words about different type of regions and different type of curves. We are talking about reducible curves for some time, and we have already derived the we have already discussed that reducible curves are those curves which can be shrunk to a point without going out of the region, and in this case, in our case, the region is simply the fluid. Okay. But quite often we will only call region or domain, because these are basically mathematical concepts. This curve can also be stated that if there are 2 points within the region or within the fluid, and if we can join them any 2 points, and if we can join them by a line without going out of the fluid or without going out of the region, and then if any 2 such curves form a closed path, this region is called simply connected or singly connected. That is the way properly this singly connected domain is defined, that if we take any 2 points within the region and can join these 2 points by a path without ever going out of the region, and if we can form 2 such paths which make a reducible closed curve, then that region is called simply connected. If not, the region is not simply connected. Now, there is degree of connectivity. When it is not singly connected, it might be say doubly connected, it might be triply connected, or it might be in general inply connected. This is called the degree of connectivity. How do we define degree of connectivity? To that, think about that we have any region or doubly connected in which there are some set of curves which cannot be shrunk to a point, which are not reducible. Now, think about that we are inserting barriers within that domain. The barriers which has no thickness, but has only 2 sides. So, in the form they are in the form of open surfaces, and if by inserting these barriers we can make the region singly connected. Now, depending upon that how many barriers are required, the degree of connectivity is defined. If we need only one barrier to make the region simply connected, then it is a doubly connected region. If we need 2 such barriers, then it is a multiply connected or triply connected region, and if we need n minus 1 such barrier, it is nply connected region. As an example, look to this, that we have, think about this region, we have an infinite cylinder and another boundary which is far away, and there is fluid in between these. You can think about the situation flow over a cylinder. Okay. If the for a solid cylinder, the solid part is of course not fluid region, that is out of the region. So, think about, let us say this is, and let us say that this is the region in the form of infinite cylinder. Now, in this case you can see that any curve, any closed curve that loops the circle, they are irreducible. The curves which do not loop the cylinder, they are reducible. So, here there are 2 different sets of curves, some curves which loops the cylinder, they are irreducible, some curves which do not loop the cylinder, they are reducible. Now, think about that we have inserted one barrier in this form. So, that this is also a boundary of the region. Insertion of this boundary still does not make this domain unconnected, different regions of the domain still are connected, they are not unconnected. This is also another requirement, that when we insert the barriers, we must not make the region unconnected. Like we cannot think about a barrier like this, then these two part, if we think about a barrier like this, that is not allowed, because that will make these two regions completely unconnected. This barrier will also be thought of as a boundary, it is no longer fluid. Now, see that just by inserting one such barrier, this region has become singly connected. Okay. You can now think of any curve that can be shrunk to a point, any closed curve. Like see, if you take about these 2 points, any two curve joining these 2 points will be these curves. These curves not crossing this, because we cannot cross, that is out of the boundary, out of the region. So, just by a simple barrier, single barrier, we have been able to make this region singly connected. So, this is called a doubly connected region. If we need 2 such barriers, it is a triply connected region. If we need n minus 1 barrier, it is n-ply connected domain. So, n minus 1 barriers, or sometimes simply called cut. Think about now that instead of one cylinder, if there are 2 cylinders, instead of one cylinder, if there are 2 such cylinders, let us say that then these are the 2 barriers that will make the region singly connected. So, this becomes 2 barriers are required. So, it is triply connected region. And you must remember that they are boundary, they are part of the boundary, they are no longer part of the fluid region, they are part of the boundary. In this case, we will mention also something which are called reconcilable curves or irreconcilable curves. Two closed curves are called reconcilable if you can make them coincide with each other by translating them, by deforming them. If you can make them coincide, then they are called reconcilable. Now, which are which cannot be made identical or which cannot be made to coincide, they are irreconcilable. Like think about this doubly connected region, this doubly connected region. Think about any closed curve which is not looping the cylinder. Think about any closed curve that is not looping the cylinder. Any such two curves you can make them identical or make them coincide by translating and deforming them, you can make them coincide. But think about two curves, one of them is not looping the cylinder and the other is looping the cylinder. You cannot make them reconcile. So, they are irreconcilable. So, in a doubly connected domain, there are two sets of irreconcilable curves. In a doubly connected region, there are two sets of irreconcilable curves. One of them, one of these sets are reducible, the other is irreducible. Similarly, in a triply connected domain, you will have three sets of irreconcilable curves, and one of them is, one of these set is reducible curves, the other two are not. So, in general, in a n-ply connected region, you will have n number of irreconcilable curves or n sets of irreconcilable curves. Out of these n sets, one set will be reducible curves, the other n minus 1 sets will be irreconcilable curves. So, whether a particular region is singly connected or multiply connected, that can be stated either by checking whether we can make it singly connected by inserting number of barriers, or by thinking that how many sets of irreconcilable curves can be drawn in this region. So, to check whether a particular region is singly connected or not, we need to think either in terms of these barriers, that whether we need to insert barriers, if so how many barriers, and then you can determine what is the degree of connectivity of that region. Alternately, you can think in terms of these reconcilable curves and see how many irreconcilable curves are possible to draw in that region, and that will give you the order of connectivity. Remember, in case of barrier, if you need n minus 1 barriers, then the region is n-ply connected. Okay, n minus 1 barriers and n-ply connected. If you are thinking in terms of irreconcilable curves, then there are n sets of irreconcilable curves in a n-ply connected region. Out of these n sets, one set is reducible curve, the other n minus 1 sets are irreducible curves. With this, now let us come back to our fluid mechanics. First of all, think about a doubly connected region, because that is perhaps the most interesting and important for aerodynamics. So, let us consider a doubly connected region, and we can make it specified. Think about an infinite long cylinder or flow over an infinite wing, a wing which is infinitely long, or flow over a cylinder which is infinitely long, and there is nothing else, only the cylinder or the wing and the fluid, that is all. So, these are an example, these are examples of flow in doubly connected region. Now, already you have stated that in this case we cannot say the potential is single valued. The potential associated with the solenoidal irrotational part of the flow field is in general not single valued. Let us see then what it is. Think about, say this is our cylinder which is infinitely long, okay. In both sides it is to infinity. Now, think about two curves which loops the cylinder, but loops only once. A curve may loop the cylinder many times, but now think about a curve which loops the cylinder only once. Okay. And if you consider two such curves, they are reconcilable. They are reconcilable, and that means you can make them coincide exactly, one overlaps the other, and for each point on one curve there will be a corresponding one point again on the other curve, which is called a one to one correspondence. That for every point on one curve you have another point, or you have a corresponding point but single point on the other curve, then it is called a one to one correspondence. Now, think about two such curves which are reconcilable and having one to one correspondence, and they are looping the cylinder just once. Then, while reconciliation, these two curves are translating. Let us say we have one curve looping the cylinder here once, another curve looping it here, and when you made them reconcile, this is also translating, that this is also translating. So, they trace out a surface. Reconciliation is something like this. Let us say this is the simplest possible thing. This is the way they have been made to reconcile. So, they formed a surface. The one that you have shown, it forms almost a cylindrical surface. But anyway, whatever these shape of these curves are, while reconciliation they will trace a surface, an open surface. Now, if you apply then the Stokes theorem, it will simply give that the line integral of this irrotational solenoidal velocity field over this curve and this curve, they are equal. That is what you can say. You cannot get them to be 0, but you can find that this is 0. Let us write. So, two curves, I will just write the main points that I mentioned in this discussion. Two curves looping the cylinder once, they are reconcilable, with one to one correspondence, with 1-to-1 correspondence. Surface described during reconciliation so then application of Stokes theorem to this open surface. Let us for simplicity call this curve path as C1, this curve as C2. This is what we can get, which we got in case of a singly connected domain to be equal to 0. In this case, we cannot find that this equals to 0, but we can find that this closed integral for any curve that loops the cylinder once have same amount of this line integral, or this line integral or this closed curve integral will be same for all curves that loops the cylinder once. Whether it is 0 or not, that we cannot definitely say. It might be 0, might not be. And in general, we will denote this value to be kappa, called the cyclic constant. In case this is 0, we will call the flow to be acyclic. If it is not, the flow is cyclic, having a cyclic constant. If we think the curve is looping the cylinder many times, then you know that after every time it loops, this integral will go on adding. So, if it loops say m times, this integral will be m times this. This integral will be m times this. M we have used for source strength, so let us forget it, say p times, then Huh. How it can loop more than once? That is quite simple. Think about again, say this is the cylinder. As many times as you want, it will go on looping. It is closed. You end these 2 points, they are closed. Here I have don't that. And it can trace the same curve again and again, that is also possible, but it is looping. If we just consider say this, the curve is now looping this cylinder many times. Now, once again we define that the potential function as before, that potential at point x at position x is the potential at position initial point 0 plus in the case of singly connected domain, if we have 2 point O and P, then this whatever path we follow, this integral would have been given, this potential would have the same function, same value, singly connected. But in this case, it may not be so. By if we let us say that O to P, this is x 0 and this is x. If we take this path, or if we take say this path, remember they are joined. The phi p at this point may not be same. The value will differ by the cyclic constant kappa. So, that is, if we evaluate phi following this path and if we evaluate phi following this path, we will get two different values of phi at point P, but which will have a difference given by that cyclic constant kappa, assuming that these paths are such that it is making one loop of closed curve. Okay. If we follow this path, say we will call this path 1, path 2, so we will call it phi p following path 1 is not equal to phi p following path 2. And phi p as the case may be. As the case may be. If the two paths make only one simple closed curve, only one loop of the closed curve, it is simply this kappa, but if it forms a complete p loop, p number of loops, then it is p times kappa. However, the gradient of phi, that is the velocity part, the irrotational solenoidal velocity part, that is still single valued. That is quite obvious, because this cyclic constant. So, gradient of phi will not be affected by this cyclic constant, gradient will remain single valued. So, even though phi is many valued, so this we have considered for 2 dimensional case. If we have an doubly connected region, we have 2 values of phi at one point, or even many valued also, if we think about the curve is looping and looping. And but the gradient of phi is still single valued, because this constant, the cyclic constant, is not affecting the gradient, the derivatives are not affected. So, phi is not single valued, but grad phi is, or we will say V equal to grad phi is. And obviously, then the once again that Laplacian phi will still remain the equation. All other behavior which you have associated with velocity field, they will remain as it is. The only thing is that phi is no longer single valued, it is associated with a cyclic constant. If in a singly connected domain, it is only one cyclic constant. If it is n-ply connected region, we need n number of cyclic constant, because we had n number of irreconcilable curves, and applying the Stokes theorem to all those n number of irreconcilable curves, we will have n number of cyclic constants. In a doubly connected region, we have only one single cyclic constant. Of course, in some cases this cyclic constant may be 0. In case it is 0, if we find such a flow in which the cyclic constant is 0, then that flow is called a cyclic, otherwise it is called a cyclic. Now, if you look back, we have already found such a flow. We have already found such a flow in which there was a single cyclic constant, or rather we consider the flow, we can say that we have considered the flow in a doubly connected region. Very nice example, that infinite line vortex that we consider. If we have an infinite line vortex, a line is basically on a limit of cylinder, a line is a limiting cylinder. So, flow about that infinite line cylinder, infinite line vortex is basically an infinite cylinder, we can think of similar situation. And if you look back to that velocity field that we obtained for a line vortex, gamma by 2 pi s, I think we wrote gamma by 2 pi s, where s is the distance from the line vortex, distance of the point from the line vortex, gamma by 2 pi s. That is essentially an irrotational solenoidal flow in a doubly connected region, and in that case the strength of that line vortex gamma is the cyclic constant. We earlier expressed in that time we expressed that that flow has a stream function associated with it, which was gamma by 2 pi log r or log s. what it was, minus gamma by 2 pi s or just gamma by 2 pi log s potential, sorry, stream function we earlier, the stream function we wrote as gamma by 2 pi s, gamma by 2 pi log s. And now you can see that we can write, can we write what should be the potential function? For that flow a potential function can be written. In that case, flow due to a infinite line vortex, the flow was only azimuthal. So, if you think in terms of r theta coordinate, we had only u theta velocity. U theta was that gamma by 2 pi r, and in terms of potential function, what is u theta? 1 by r d phi d theta. The velocity is gradient of phi. The velocity is gradient of phi, and in r theta coordinate the gradient is d phi dr, the r component is d phi dr and the theta component is 1 by r d phi d theta. So, 1 by r d phi d theta equal to gamma by 2 pi, say s we can call r, minus, which is minus? Minus gamma by 2 pi. Oh, this one is, this one was minus gamma by 2 pi log s. So, what will be phi for that? S we can write r also, it is r matters. Phi is how much? How much? Gamma by 2 pi. 1 by r d phi d theta is gamma by 2 pi r. D phi d theta is gamma by 2 pi. So, phi is gamma by 2 pi theta. 1 by r d phi d theta is gamma by 2 pi r. Gamma by 2 pi r is what we have derived last time. So, for that where this r theta plane is normal to the line vortex and theta is the angle taken anticlockwise in that plane. If you have an infinite cylinder, the r theta is normal to that and theta is taken anticlockwise in that plane. Theta equal to 0 is of course arbitrary. Now, I do not know whether a question should come to your mind that we have mentioned or we have seen that this potential phi is defined when the flow field is irrotational. We have said if the curl of the velocity is 0, then the velocity is gradient of a scalar potential. So, the velocity potential is basically defined when the flow is irrotational. If the flow is not irrotational, then you cannot define a velocity potential. It is not that for all flow there is a velocity potential, no. If the flow field is irrotational, only then you have a potential. All flow field are not potential flow field. Then line vortex, you know that vorticity is associated with rotation. The rotational part of the velocity, that is what we called vorticity. Then if the flow is due to a line vortex, which is associated with rotation, how can we have phi of velocity potential? The answer is simple. If you remember that what is this line vortex? We have considered that there is a singularity in vorticity distribution, and the singularity is such that there is no vorticity anywhere in the flow, but only on that line, and for an infinite line it is equivalent to a two dimensional case. So, in a two dimensional only at that point, everywhere else there is no vorticity, but only at that point there is the concentration of vorticity. So, essentially this potential, the flow field is not rotational only at that, not irrotational only at that point, everywhere else it is irrotational. Just because that there is a vorticity does not make that the flow field is rotational everywhere. The flow field is rotational only on that line, or in two dimensional case only at that point. Everywhere else it is irrotational. Of course, the flow field is solenoidal. So, flow due to a line vortex is solenoidal and irrotational everywhere except on that line or on that point in two dimensional flow, everywhere else. So, now, we will see now that what is the necessary condition for a particular flow field to be determined uniquely in a doubly connected region. We have already seen it for a singly connected region, but we would like to see what will happen in case of a doubly connected region. And uniqueness we can very simply state it this way, like say that we have two solution, and let us say that they have same value of the cyclic constant, both the flows have the same values of the cyclic constant. Now, since the Laplace equation is a linear equation, what we have mentioned already, the sum of these or difference of these two solution is also a solution. So, if you have two solutions which have same values of cyclic constant, then the difference of these two solution is a cyclic. There is no cyclic constant associated with that. We have phi 1 which is associated with the cyclic constant kappa, another solution phi 2 which also has the cyclic constant kappa. Then if we subtract these two, then that phi 1 minus phi 2 will have no kappa, and again we know what would be the condition that phi 1 minus phi 2 that will be satisfied, that should be satisfied. Again the same condition what we have found for singly connected domain, because in that case the solution is like a singly connected domain solution. If there is no cyclic constant, the solution is same as the solution in a singly connected domain. So, if you have two solutions from there with same cyclic constant, from there we can see that the same condition what were necessary for flow to be determined uniquely in a singly connected domain, they are also required if the region is doubly connected. Okay. But we have already imposed another condition, that the two solutions have same value of cyclic constant. So, if the two solutions have same cyclic constant, or if the cyclic constant is fixed, then we need the same condition what we needed for singly connected domain, and we can say that in a doubly connected region we need an additional condition other than those conditions that we had in a singly connected domain. We have an additional condition that the cyclic constant must be specified. If we want to find the solution uniquely for a particular problem, we must know the cyclic constant specifically along with those other boundary conditions.